Hi, in this video, I will explain to you how to visualize regular expression using a finite state automaton. The idea is pretty neat that given a regular expression, using the regs tool from Microsoft, we can visualize how the regular expression will behave at runtime. Regular expressions are tricky to analyze statically, so it's good to see from a graph perspective how it looks like. So what you're seeing is an extremely simple regular expression that I will zoom in a little bit. So what you're seeing is extremely simple regular expression. It accepts characters A through F, right? Both upper and lower case, as well as numbers from 0 to 9, okay? And this 2 means it expects 2 characters from this group of characters that are listed here, okay? And then it also accepts a colon, but the colon is optional because there is a question mark. Okay, so we wanted to see graphically what it means. Okay, given this regular expression, what it means. So we can actually run the tool now, and we get a regular expression like this. Okay, what you're seeing is a small regular expression converted into an automaton. Let me explain the structure of the automaton a little bit. So you're in some state, okay? This is the initial state where you see an arrow mark pointing to number 3. This is an initial state. All characters that you feed in will not change the state of the automaton. So it will stay in state 3. However, the automaton may also go to state 0. This is an empty transition, okay? We call it epsilon transition. And then it will start matching your characters in this set of numbers from 0 to 9, capital A to F, small a to F, only one character. And the same with this one, second character. And now the automaton is forking, right? Because the reason for the fork is that what is the meaning of colon? The colon is basically one of the characters you would like to accept, but it's optional. That's the reason why we see a fork. Okay, that's the reason why we see a fork here. And then again we go to state 5 and we take an empty transition, right? That's the reason why you see an empty bracket, closed bracket, and open bracket, empty transition, epsilon transition to state number 6, which is double circled to denote it is a final state. And there is a loop there. That means it will also accept anything after that, right? And if you put in, say, for example, if your input is, say, XYZ, right? And then let's say 09, okay? What will happen to this input? The XYZ will loop here, right? It will stay at state 3. So these 3 elements have no effect. We are still staying at state 3. And then taking an empty transition, we go to this state. And now our automaton is matching the character 0, which is allowed character. So it's going to get into step 1. And that step 1, it is going to match the character 9, which is allowed here. And now the automaton is at state 4, but we don't have any more inputs. So it's going to take an empty transition and reach state 6. That means XYZ09 will be accepted by this automaton because we will reach this final state. When we don't reach the final state, that means something is wrong in our input. The input doesn't reach the last state, okay? All right, that's basically what it means an automaton to accept a string. Now, we can also reason about these little loops that are very interesting, okay? What about input like this? Say I start with 09, right, which is perfectly fine. I will have 0 matching here, 9 matching here. And now I put XYZ. What will happen now? Will it match this automaton or not? It does, right? Because 0 is putting us to state number 1. 9 is putting us back to state number, well, it is putting us to the state number 4. and then we take an empty transition, and now we are at state number 6. Okay, at state number 6, we accept X, Y, Z, so we will stay here. So this is also accepted by the state machine. Okay, so how do we sort of avoid, if the goal is to avoid these loops which accept anything? Essentially, from a programmatic perspective, we are basically doing substring matching in this design, right? With loops, we are doing substring matching. So let's go back to the automaton and make it stronger, so we don't accept substrings. Okay, how do we do that? All we have to do is actually very simple, right? We put a cap at the beginning and a dollar at the end, and now the automaton must look different. There should not be loop. Let's see what happens now. The automaton must not have a loop. That's what I'm expecting now. As soon as it comes out, I'll show you. For some reason, it's kind of slow. Let me rerun this. Yeah. Okay, so we have the automaton now. Now I will zoom in a little bit. As you can see here, now there is no loop at state number 0, nor at state number 4, nor state number 3. Let me explain why we have suddenly two double circles, okay, state 3 and state 4. The reason being that our automaton will start at 0 state, state number 0. And if we feed in an input, say 0 and 9, so this 0 will go to, well, we start at state number 0. As soon as we feed in 0, it is one of the allowed characters, so we will get into state number 1. And now we are parsing 9. 9 is matching here, so we will be at state number 3. And remember, state number 3 has 2 circles. That means this is accepted state. Okay, this is accepted. Okay, what about this input? 0, 9, a colon. This is also accepted input, because 0, 9 will put us at state number 3, and a colon will match the colon here. That's the reason why we have 2 circles. This is all 2 circle nodes are accepted state nodes. Okay, that's basically the semantics. All right, so what shall we do now? We can go back here and look at this regular expression and make some minor changes. Let's say we would like the pattern to repeat multiple times. Let's say we want this to repeat 2 times. Okay, so how do we do that now? Well, we just go and generate the graph, and the graph should come out anytime soon. So it has come out. So now it's becoming more interesting, because the colon is an optional part. So there's a fork, as we discussed earlier. And as you can see, the same structure is repeated 2 times. Right? The same structure is repeated 2 times, because we said repeat 2 times. Okay, so what I'm going to do is show you. Here it is, right? Now this structure is shown here for you. It's going to accept now. Let me write some example acceptance. It will accept say 0, 9, right? It's going to accept 0, 9. 0 will be here, 9 will be here. So we are at state 3 now. And then we can take either a colon path. Let's put a colon just to take this route, colon. And then we put, again, these 2 are empty transitions, right? The colon is optional. Okay. And now we can put, say, 8, A, which is perfectly fine, because 8 is accepted here and A is accepted here. Now we are at state 7. So this is valid regular expression. Okay. All right. So you got the idea of how we can visualize the automaton. And important thing is that by putting a dollar at the end, we avoid the loops. and also putting a cap at the beginning, we avoid accepting substrings. Okay, so when I say accepting loops, I mean to say we are very strict. We don't accept substrings. Okay, earlier we would have been accepting even this, right? Now this is not going to be accepted because X is not part of the accepted allowed characters here. So the automaton will get stuck at state number 0, so which is not the accepted state. All right, that's basically what I wanted to share to you. This is a nice way to visualize a regular expression. You may have complex regular expressions like validating IP address, MAC address, email address, and so on. Basic regular expressions can be visualized using this technique. Regular expressions have been extended over the period of years, and there are some non-standard extensions. I don't believe this tool will analyze non-standard extensions. I have tried some which didn't work. Okay. The idea of converting regular expressions to automata is a very old idea in theory of computation, at least 70 years old. I have read papers in 1956 papers that talk about this mapping. Okay, thank you very much. That's all.